We generalize the preceding calculation. If this is a mass big M with radius big R, then the work from radius big R out to radius little r we obtained by a similar integral to the one we just did. And there are the details. Well, there's the integral, there's the result. If you know the calculus, you can work out the details. The point here, though, is as r goes to infinity, as we move further and further away, approaching infinity, then our delta W, our work difference, the work done between here and here, can be found by letting little r approach infinity, and that's just big G big M little m times 1 over r, since this thing goes to 0. So that our work from here to here is big G big M little m times 1 over r minus 0, which is big G big M little m over r. It follows that when the kinetic energy at the surface is equal to this, plus whatever we need to overcome atmospheric drag, which will be non-trivial, actually it'll probably burn us up, almost certainly burn us up. I don't think there's any known substance that will allow us to escape the Earth, at least with human beings intact, by firing something at this velocity. Anyhow, if our kinetic energy is great enough to equal this at the planet's surface, and if you ignore air resistance, then you can escape to infinity, to as far as you want, in other words. There's no limit to how far you'll go if you have this velocity, or if you have this kinetic energy when you leave. That is, again, called our escape velocity. For a planet of mass big M and radius big R, this is a formula for the escape kinetic energy, and we can easily solve that to obtain our escape velocity by setting 1/2 mv squared equal to the escape kinetic energy and solving for v. Multiply both sides by 2, that's where the 2 comes from. The m will divide out, and you end up with 2gm over r. Now remember that a planetary orbit, a low Earth or low planet orbit, an orbit close to the radius of the planet, gives us a velocity of the square root of gm over r, which compares with the other expression. We've just got a 2 in this expression, or we've got no 2 in this expression. Okay? For Earth, the velocity of escape, v escape, is approximately 11,800 meters per second. The orbital velocity, low Earth orbital velocity, is approximately 8,000 meters per second. And we can see that we just blasted John Glenn into space and brought him back. We had to get him up to 8,000 meters per second. Had we wanted to get rid of him, which we didn't want to do, of course, we could have just given him a velocity of 11,600 meters per second, and he'd have never come back. I think there's some world leaders, one in particular right now, that a lot of people would like to do that to.